There we go. So today, I want to do problems on Bernoulli equations and homogeneous equations. So these are nonlinear first order equations. That can be reduced to linear equations. So let me review Bernoulli equations, and then I'll do some of the homework problems. And after that, I will review the homogeneous equations and go over some of the homework problems there. So let me try to pull up the parts of the book that we're going to go over. Actually, we're going to reduce these equations to not necessarily linear, but separable equations. That's really the key thing. So are there any questions before we start? Okay. So a Bernoulli equation is the first order equation of the following form: y prime plus p of x y. Now, if this were equal to f of x, this would be linear, but it's f of x times some power of y. And of course, if r is 0, this is just f of x, it's linear. If r is 1, you can just bring this over to the left-hand side and you have a homogeneous linear equation. So this is nonlinear if r is different from 0 or 1. And the technique for solving this equation is the following. Let y1 be a solution of the complementary homogeneous equation y prime plus p of x y equals 0. And then we look for a solution y of the form u times y1. So in that case, if we differentiate y prime is u prime y1 plus u y1 prime. And if we plug into our equation, what we get is y prime, that's u prime y1 plus u y1 prime, plus p of x times y is u y1, equals f of x times y to the r, that's u y1 to the r. So if I factor the u out of these two terms, I get u prime y1 plus u times y1 prime plus p of x y1 equals f of x u to the r y1 to the r. But of course, this is 0. Of course, we chose y1 to be a solution of this homogeneous equation. So we get u prime y1 equals this. If we divide by u to the r, we get u prime over u to the r equals f of x y1 to the r divided by y1 is y1 to the r minus 1. And this equation is separable, and we can try to solve it. Okay, so that's an approach to dealing with a Bernoulli equation. And in the homework problems, the first couple were Bernoulli equations. So let's look at the homework. So this is on page 68, number 1. Solve the equation y prime plus y equals y squared. So this is a Bernoulli equation. Remember, if you think of the general Bernoulli equation as being y prime plus p of x y equals f of x y to the r, in this case, my p of x is just equal to 1. My f of x is also equal to 1, and r is equal to 2. So the complementary equation, that's just the homogeneous equation, y prime plus y equals 0. The solution is y1 equals e to the minus x. And that's just, if we let y equal uy1, which is u times e to the minus x, and plug into this equation and try to solve for u, let's see what happens. You get y prime is u prime e to the minus x plus u times the derivative of e to the minus x, which is minus e to the minus x, plus y plus u e to the minus x equals y squared. U squared, that's u e to the minus x squared, or u squared e to the minus 2x. And you see, of course, that here I have minus u e to the minus x plus u e to the minus x. That's 0. It's just because e to the minus x is the solution of this differential equation. So I have to find u prime e to the minus x equals this. That is, u prime over u squared equals e to the minus x. Right? And this is a separable differential equation. If I integrate the left-hand side with respect to u, I get minus 1 over u. If I integrate the right-hand side with respect to x, I get minus e to the minus x plus a constant. So 1 over u is multiplied by minus 1. E to the minus x minus a constant, u is equal to 1 over e to the minus x minus a constant. And y is u e to the minus x. So I multiply this, I get e to the minus x over to e to the minus x minus a constant. Or I can multiply the numerator and denominator by e to the x, and I get 1 over 1 minus c e to the x. And that's the solution. Any questions about this? Let's just check. So this is supposed to be a solution of my differential equation. So y prime plus y, this is y. So if I differentiate this, this is 1 minus c e to the minus x to the minus 1. So that's minus 1 minus c e to the minus x to the minus 2 times the derivative of 1 minus c e to the minus x, which is the derivative of c e to the x, the plus here, 1 minus c e to the x. The derivative is minus c e to the x plus y, plus 1 over 1 minus c e to the x. So what is that? That's, let's see, this is c e to the x over 1 minus c e to the x squared plus 1 over 1 minus c e to the x. If I put this over a common denominator, 1 minus c e to the x squared, I get c e to the x plus 1 minus c e to the x. These cancel. I get 1 over 1 minus c e to the x squared, and that's exactly y squared. So y prime plus y equals y squared. So that's my check that everything is good. Any questions about this? This is, this is solving differential equations. It requires some mathematical technique that you develop by working at problems for hour after hour, really. Okay. That's problem number 1 from the homework. I think then we had problem number 2. Problem number 2 is to solve the equation 7xy prime minus 2y equals minus x squared over y to the 6th. So this is not exactly in the form of a Bernoulli equation because I don't have y prime, I have 7xy prime. But for x different from 0, I can divide by 7x. I get y prime minus 2 over 7 y over x equals minus, I'm dividing by 7x, so I get x over 7x to the 6th. Maybe I should write this like this. I mean, this is exactly right, but it's when I divide by 7x, I get minus 2 over 7x times y. So again, if you compare this to the general form of the Bernoulli equation, which is y prime plus p of xy equals f of x y to the r, my p of x is this, minus 2 over 7x. Oops, y. And then maybe I should write y to the 6th. So this is minus, divided by 7, minus x over 7. Y to the 6 is y to the power minus 6. So p of x is minus 2 over 7x. F of x is minus x over 7. And r is minus 6. Okay. So now this is of the form of a Bernoulli equation with this value for r. We never said r had to be positive. Doesn't have to be. So step 1, solve the homogeneous equation y prime minus 2 over 7x y equals 0. So this is separable equation. This is y prime equals 2 over 7x y, or y prime over y equals 2 over 7x. And if we solve this equation, what do we get for y1? We get, when we integrate, the log of y1 is 2/7 times the log of x. So one solution of the homogeneous equation, when you exponentiate, is y1 equals x to the 2/7. So now I let y equal uy1, which is u times x to the 2/7. And let me plug this into my differential equation. Y prime minus 2/7xy. Y prime is u prime x to the 2/7 plus u times the derivative of x to the 2/7, which is 2/7 x to the minus 5/7, minus 2/7x times y, which is u x to the 2/7, equals minus x/7 y to the minus 6. So this is 1/y to the 6th, 1/u to the 6th. So this is 1/y to the 6th. That's 1/u x to the 2/7 raised to the 6th power. Now notice here, I have 2/7 u x to the minus 5/7. X times x to the 2/7 over x is x to the minus 5/7. Again, this cancels. This is equal to 0. So I have u prime x to the 2/7 equals minus x/7, 1/u to the 6th, x to the 2/7 of the 6th, that's x to the 12/7. And x/x to the 12/7 is x to the 5/7. So this is minus 1/7 x to the minus 5/7 times 1/u to the 6th. So if I multiply by u to the 6th, I get u to the 6th u prime. If I divide by x to the 2/7, I get minus 1/7 x to the minus 1. Right? 1/x to the 5/7, 1/x to the, this is 1/x. So I have this very simple separable equation to solve. When I integrate, I get 1/7 u to the 7th equals minus 1/7 log x plus a constant. So u to the 7th, just multiply by 7, is minus log x plus 7 times a constant, which is just another constant. So u is the 7th root. U is c minus log x to the 1/7. And y was equal to x to the 2/7 times u. So we get x to the 2/7 c minus log x to the 1/7 power. And that is the solution of the Bernoulli equation. Okay. And you can check by plugging into the original differential equation and seeing that it works. Let's see. I think the next homework problem was number 7, then number 9, then 15. Okay. Okay, so next is problem number 7. And number 7 is an initial value problem. We want to solve the equation y prime minus 2y equals xy cubed with the initial condition that y at x equals 0 has the value 2 root 2. So we first look at the homogeneous equation y prime minus 2y equals 0, and the solution of that is y1 equals e to the 2x. So then we let y equal uy1, which is u times e to the 2x. And y prime then is u prime e to the 2x plus 2u e to the 2x minus 2y minus 2u e to the 2x. So of course this cancels, that's just 0, equals xy cubed, which is x. Y cubed is u cubed e to the 6x. So I have u prime e to the 2x equals xu cubed e to the 6x. So if I divide by e to the 2x, I get u prime is xu cubed e to the 4x. And this is a separable first order differential equation. U prime over u cubed is equal to x e to the 4x. I can divide for where u is different from 0. So we integrate. The integral of 1 over u cubed du is minus a half 1 over u squared. And the integral of x e to the 4x dx, if you integrate by parts, you get x e to the 4x over 4 minus e to the 4x over 16 plus a constant. Right? If you differentiate this, you get e to the 4x over 4 plus x e to the 4x minus e to the 4x over 4. So this is integration by parts. So I can now solve this equation for u squared. Let's see, let me just multiply by minus 2 to make this a little bit easier. 1 over u squared equals e to the 4x over 8 minus x e to the 4x over 2 plus a constant. Right? I'm multiplying by minus 2. And if I want to remember, y is u e to the 2x, y squared is u squared e to the 4x. So just to be a little bit quicker, if I divide by e to the 4x, I get 1 over u squared e to the 4x is equal to an eighth minus x over 2 plus c over e to the 4x. And this is 1 over y squared. So y squared is equal to the square root of this whole thing. Reciprocal. So 1 over, so y is the square root of an eighth minus x over 2 plus c over e to the 4x. But this is an initial value problem. I have an initial condition that y of 0 is 2 root 2. So if I let y equal 0, 2 root 2, which is y of 0, is 1 over the square root of 1/8 0 plus c. Y squared is equal to this. So y one over u squared is e to the 4x over 8 minus x e to the 4x over 2 plus a constant. That's all 100% correct. And so what is c? So if I square both sides, just to make it easier, when I square this, I get 8 equals 1 over an eighth plus c, which means c has to equal 0. And then 1 over an eighth is 8. So c is 0. So here's the solution of my equation with c equal to 0. So what I get as the answer is just y equals 1 over the square root of 1/8 minus x over 2. And maybe I'll just simplify that a little bit. So this is for problem number 7. Y is equal to, this is solving the initial value problem, 1 over the square root of 1/8 minus x over 2. Let me simplify that a little bit. So this is 1 over the square root of an eighth times 1 minus 4x, right? Because 4 over 8 is 2. And this is 1 over 8 is the reciprocal. This is 1 over 2 root 2. I get 2 root 2 over the square root of 1 minus 4x. So for my differential equation, y prime minus 2y equals xy cubed, with the initial condition y of 0 equals 2 root 2, I get the solution that y is equal to 2 times the square root of 2 over the square root of 1 minus 4x. And again, you can check. First, when you let x equal 0, y at 0 is 2 root 2 over the square root of 1 minus 0, which is 2 root 2, so that checks. And what about solving this differential equation? Let's check that. Right? So y is 2 root 2, 1 minus 4x to the minus a half. So y prime is 2 root 2. The derivative of this is minus a half, 1 minus 4x to the minus 3 halves, times the derivative of 1 minus 4x, which is minus 4. So I get these twos cancel. I get minus times minus is plus. So root 2, I get y prime is equal to 4 root 2, 1 minus 4x to the minus 3 halves. So y prime minus 2y is 4 root 2, 1 minus 4x to the minus 3 halves, minus 2y, which is minus 4 root 2, 1 minus 4x to the minus a half. This is equal to 1 minus 4x to the minus 1, 4 root 2. No, sorry, that's what this is equal to. Let's calculate xy cubed. Xy cubed is x times, what is y? 2 root 2 over the square root of 1 minus 4x cubed. So this is equal to x. I have a 1 minus 4x to the minus 3 halves, 2 root 2 cubed. I'll just write this as x, 2 root 2 cubed. Let's see. This I can write as 4 root 2, checking is harder than solving the problem. 1 minus 4x to the minus 3 halves times 1 minus 4x. Aha. So this is, the ones cancel, I get 16 root 2x times 1 minus 4x to the minus 3 halves. 2 root 2 cubed is 8, is 16 root 2x, 1 minus 4x to the minus 3 halves. It is a miracle, but this does check. Okay. Any questions about this? Again, this is calculus, and we have an exam in a month or so, and you're going to on campus. So you're going to sit down and have to solve correctly differential equations like this. All right. What about the second type of differential equation that we convert to a separable equation? Those are homogeneous equations. So a homogeneous equation, so this is the second use of the term homogeneous. It's not an equation where the right-hand side is 0. It's a differential equation where y prime is some function of x and y, but in fact, this function only depends on the ratio of y over x. So for example, if we have a differential equation, y prime equals y plus x e to the minus y over x, you can just simplify this. This is y over x minus e to the minus y over x. And this only depends on y over x. If we let u equal y over x, this is u e to the u minus e to the minus u. Or second example, we let y prime be y squared plus xy minus y squared minus x squared over x squared. If you rewrite this polynomial on the rational function on the right, this is y over x squared plus y over x minus 1. So again, if you make this substitution, u equal y over x, this is u squared plus u minus 1. This is some function of y over x only. And then you let y equal u times x, and you will always get a separable equation. So there were several homework problems involving homogeneous equations, and the first is number 15. So number 15, we have the differential equation y prime equals y over x, y plus x over x. Which is y over x plus 1. So this is homogeneous. And we look for a solution of the form y equals u times x. So what do you get? You get y prime is u prime x plus u equals y over x, which is u plus 1. So we have to solve the equation. The u's cancel. U prime x equals 1. Or u prime equals 1 over x for x different from 0. That means u is log x plus a constant. So y is u times x is x log x plus c times x. That's the solution. Right? So we had y prime is y plus x over x, which we can write as y over x plus x over x, which is 1. So this is homogeneous. Just the right-hand side is just a function of the ratio y over x, and we call that u, so we're letting y equal u times x. When you make that substitution, you end up with just the equation u prime is 1 over x, so u is log x plus a constant multiplied by x, and we're done. Any questions about this? Number 16. We have y prime equals y squared plus 2xy over x squared. That looks complicated until you separate this out and you write this as y squared over x squared plus 2xy over x squared, which you see is y over x quantity squared plus 2y over x. So again, we let u equal y over x, or y equals ux. So y prime is u prime x plus u equals u squared plus 2u. So you subtract u from both sides, u prime x equals u squared plus u. So for u not equal to 0 or minus 1, I can divide by u squared plus u. I get u prime over u squared plus u equals 1 over x. Suppose u does equal minus 1. That means y over x is minus 1, so y equals minus x. And you can check, y equal minus x is a solution of this differential equation. X different from 0, you can't divide by 0. But if you let y equal minus x, y prime is minus 1, y squared plus 2xy over x squared is x squared minus 2x squared over x squared is minus 1. This checks. So this is a solution of the differential equation. Right? If u is equal to minus 1, you get y equals minus x. If u equals 0, then y is 0. That's a trivial solution. If you have y equals 0, you also get a solution. You have y equal minus x, you get a solution. For u different from 0 or minus 1, we'll get a third solution. U prime over u squared plus u equals 1 over x. So the integral of 1 over u squared plus u du, this is the integral of 1 over u times u plus 1 du. Let's see, if I expand this in partial fractions, this is the integral of, see, 1 over u minus 1 over u plus 1. So this is u plus 1 du. Yeah, that's right. So this is the log of u over u plus 1. And that equals the integral of 1 over x dx, which is the log of x plus a constant. Put this case plus a constant. So if I exponentiate, I get u over u plus 1 equals some constant times x. And I should be able to solve this equation for u. This says, let's see, u plus 1 over u. If I take the reciprocal, which is 1 plus 1 over u, equals 1 over c times the absolute value of x. So if I make u and x positive, I get 1 over u is 1 over cx minus 1. So u is, so this is 1 minus cx over cx. So u is cx over 1 minus cx. And y is u times x, which is cx squared over 1 minus cx. And that's the solution. Let's see, everyone's so quiet. Let me just go through this again, because there's a technique here and it's important to understand. I mean, you have to learn how to solve this type of problem. So problem 16, solve the equation explicitly. Y prime equals y squared plus 2xy over x squared, which is y squared over x squared plus 2xy over x squared, which is y over x squared plus 2y over x, which is u squared plus 2u, if we let u be equal to y over x. And then y prime is ux prime. That's u prime x plus u x prime, which is 1, equals u squared plus 2u. So u prime x equals u squared plus u, which is u times u plus 1. Now, I can divide if u is different from 0 or 1 or minus 1. If u, which is y over x, is minus 1, then y is equal to minus x is a solution of this differential equation. If you plug in y equals minus x, you get a solution. So, but if u is not equal to 0 or minus 1, then my differential equation becomes simply u prime over u plus 1 equals 1 over x. Sorry, u prime over u times u plus 1 is 1 over x, which means if I integrate the log again, the integral of 1 over u times u plus 1 du is the integral of 1 over u minus 1 over u plus 1 du. This is the log of u over u plus 1. Or minus the log, or minus the log of u plus 1 over u, or minus the log of 1 plus 1 over u. And this equals the integral of 1 over x dx, which is the log, the absolute value of x, plus a constant. So this is log of x plus a constant. So the log of 1 plus 1 over u multiplied by minus 1 is the log of 1 over x plus a constant. So if I exponentiate, 1 plus 1 over u is some constant times x. Keep going. You get exactly the same solution we got a moment ago. Cx squared over 1 minus cx. Now, the book emphasizes the fact that when you have a solution, when you have implicit solution involving an equation of u equals to some equation in x, or some function of u equals some function of x, you cannot necessarily solve for u. So sometimes you can only get an implicit solution of the differential equation. So problem number 22, for problem number 22, it says solve the initial value problem. So let me do that. This is problem number 22. We have the equation y prime equals xy plus y squared over x squared, and the initial condition that y at minus 1 is equal to 2. If I expand this, this is xy over x squared, this is y over x, plus y squared over x squared, which is y over x squared. So this is of the form u plus u squared. This is homogeneous. So if I let y prime equals ux, if I let y equal ux, then y prime is u prime x plus u equals u plus u squared. That just says u prime x equals u squared, which is 1 over u squared u prime equals 1 over x. When you integrate 1 over u squared, you get minus 1 over u equals log x plus a constant. So if I take the reciprocal, u is equal to 1 over minus sign, right, this is c, minus log x. And so y, which is u times x, is x over c minus log x for some constant c. And now we have our initial condition, y of -1. If you let x equal -1, I get -1 over c times log 1, which is 0, equals 2, which means c is -1/2. Which means y is equal to x over -1/2 minus log x. Or I can write this as minus 2x over 1 plus 2 log x. So in this, if I let x equal -1, I get +2, and this is a solution of the differential equation. Any questions about this? Well, let's keep going. Number 28. So for number 28, it says, solve the given homogeneous equation implicitly. So for number 28, the equation is y prime equals x plus y over x minus y. Now this doesn't look homogeneous at first glance, but if you factor an x out of the numerator, you get x times 1 plus y over x. If you factor x out of the denominator, you get 1 minus y over x. And these x's cancel, at least for x different from 0. So you get 1 plus y over x over 1 minus y over x. So now this is homogeneous because this only involves the ratio y over x. So we're going to let y over x equal u, or y equal u x. So we get y prime, which is u prime x plus u, equals 1 plus u over 1 minus u. So x times u prime is 1 plus u over 1 minus u minus u. You put this over a common denominator of 1 minus u, I get 1 plus u minus u times 1 minus u. I get 1 plus u minus u plus u squared over 1 minus u. So if I bring the u's over to the left and the x's to the right, I get 1 minus u over 1 plus u squared, u prime, equals 1 over x. Can I integrate 1 minus u over 1 plus u squared? Let's see. The integral of 1 minus u over 1 plus u squared du is the integral of 1 over 1 plus u squared minus u over 1 plus u squared. The integral of 1 over 1 plus u squared is the arctangent of u, and the integral of u over 1 plus u squared is the log of 1 plus u squared. So if I differentiate this, I get 1 over 1 plus u squared times 2u, so I need a factor of 1/2. And this is going to equal the integral of 1 over x dx, which is log x plus a constant. So I have arctangent of u, which is y over x, minus 1/2 times the log of 1 plus u squared, which is y squared over x squared, equals log of x plus a constant. Let's see, let me write this differently, simplify it a bit. So I have arctangent of y over x minus a half times the log. This is x squared plus y squared over x squared. So this is arctangent of y over x minus a half times the log of x squared plus y squared plus a half times the log of x squared, which is the same as a half times 2 times the log of x. This is the same as the log of the absolute value of x equals log of the absolute value of x plus a constant. So these cancel, and I get that for this differential equation, the solution y of x satisfies arctangent of y over x minus a half log of x squared plus y squared equals c. So this is the implicit solution of this differential equation. I cannot solve this equation for y. It's not just that I personally can't do it. It can't be done in terms of any of the functions that we know. You can graph the solution of this numerically. So for example, if you use Maple, Maple will draw the integral curve of this equation, but you can't do it. Actually, I'm rather curious. Let me just go to Maple for one moment. If you don't know or have Maple, that's fine, but there is something called Maple. And let me, for the moment, share screen with this. So here you should be looking at a Maple window. And there's a command package in Maple called plots. Let me say with plots. And now there are a lot of plots I can use, and the one I'm interested in is implicit plot. And what I want to plot implicitly is arctangent of y over x minus a half of the log of x squared plus y squared equals a constant. Let's just say equals 1, see what happens. Let's say x goes from minus 10 to 10, and y goes from minus 10 to 10. We might adjust these, but so we get a curve that looks like this. So this is an integral curve of this differential equation. So on any part of this curve where you have y as a function of x, that is a solution of the differential equation. sort of curious about what this thing really looks like. Yeah. Okay. In any case, if you have maple, you can actually graph the integral curve, but that's what it is. Okay. Any questions about this? Maybe I'll do one more. Let's see. I'll try number 32. That was the last problem on the homework. Problem 32, we have an equation y prime equals y over y minus 2x, which if you divide numerator and denominator by x, you get y over x minus 2. So this is of the form u over u minus 2 if you were to let u equal y over x. So y prime equals u times x. Y prime is u prime x plus u equals u over u minus 2. This is a homogeneous differential equation. And if I let u equal y over x, I get this differential equation. So x u prime is u over u minus 2 minus u. If I put this over a common denominator of u minus 2, I get u minus u times u minus 2, which is u minus 2u, which is u minus u squared over u minus 2. So if I rearrange this, I get u minus 2 over u squared over u minus u squared, which is u times 1 minus u prime equals 1 over x. So I have this separable differential equation. All right, let me just double check. Y equals y minus 2x. So y over x is y over x. So this is y over x minus 2. So that's u over u minus 2. So u prime x plus u is this. So u prime x, or x u prime, is u over u minus 2 minus u. So that's u minus, this is u minus 2, minus u squared, plus 2u. So that's 3u. Glad I checked. Over u minus 2. So this is 3u. So this is u minus 2, when I bring this over to the other side, over 3u minus u squared, which is u times 3 minus u, equals 1 over x. So I want to integrate this to find u. So I want to expand u minus 2 over u times 3 minus u into partial fractions, say a over u plus b over u minus 3. Say it's same as 3 minus u. So, or so u minus 2 is going to be a times 3 minus u minus b times u. Let's see. By that u equals 0, I get minus 2 equals 3a. So a is minus 2/3. If I let u equal 3, I get 1 is minus 3b. So b is minus a third. So if this is correct, u minus 2 over u times 3 minus u is equal to minus 2/3, 1 over u, minus 1/3, 1 over u minus 3. So this, I believe, is correct. So the integral of u minus 2 over u times 3 minus u du is the integral of this, which is minus 2/3 log u minus 1/3 times the log of u minus 3. And that's going to equal log x plus a constant. Or another way of writing this is, same way actually, but the log of u minus 3 minus 2 times the log of u, I'm just multiplying by 3, is 3 log x plus a constant. U is y over x, so I get the log of y over x minus 3 minus 2 times the log of y over x is 3 log x plus c. And let me see if I can do a little bit better than this, because this is the log of u minus 3 over u squared equals the log of x cubed plus c. So yeah. So u minus 3 over u squared is some constant times x cubed, and you can plug in y over x for this and get some expression. But what would you get? Y over x minus 3 or y over x squared. If you multiply by x squared, you would get xy at x times y minus 3x. In any case, you can, there are various ways to rewrite this, but this is an equation that can only be solved implicitly. You can't solve for y in terms of x. It's too complicated. Okay. So these are examples of Bernoulli equations and homogeneous equations. And this is for us the end of chapter 2. So you should work on these homework problems, and next week we will start second order equations. Okay. Remember, the next class is a week from today, next Wednesday. Any questions before we end? If not, okay, all. Have a good day.
Hey, Professor,
Yes,
I have a question. Is it possible to send you one of my questions that I just put a homework and see what I did wrong?
yes.
Okay,
Yeah,
thank
if
you.
you can put it in an email, then I'll get it easily.
Okay.
All right. Bye all.